I think to this presentation as normal. Please let us quickly start and have your presentation. After which we are going to have first questions and observations.
Oh,
Thank you. Good morning and welcome for to this presentation.
thank you very much, Mr. Chown. Good morning, everyone. Let me first of all apologize for the starting late. No, these are things sometimes. I said everything since yesterday. Just this morning, I tried to put on the gen. It was misbehaving, and you know how we are facing issues with light in this country these days. Can you people hear me?
We are hearing you. We are hearing you. Just
And
go
you
ahead.
can see my slides, right?
We are seeing it clearly.
Yes, yes.
So, good morning once again, everyone, Mr. Chairman, and everyone present. I greet you. My name is, as been introduced by the chairman and the secretary himself. My name is MAJada Aliyu. I'm from Department of Mathematics, Lamido University, Kafin House here in Jigawa State. Thank you for sharing.
Sagir, please
Uh,
off your mouth.
I am, as rightly said, currently a PhD student at Nigerian Defense Academy under supervision of Associate Professor Bashir Ali. The title of our presentation today is on the ranks of semi-group of order preserving or reversing partial contraction mappings on the finite chain. Of course, since it is PhD work, it's a joint work between myself and my supervisor, as well as also Dr. Mansour Zubair. So you can rightly say it's a joint work between an academic father and his two academic sons. This work has not been published yet, but it's been archived. It's there online. We are thinking of publishing it very soon. So any suggestions, comments, and contributions are highly welcome to enrich the work. This is the outline of our presentation. In this work, we study two sub-semi groups of contraction mappings on the finite chain 1 to n, the semi-group of order preserving partial contraction mappings and that of order preserving order reversing. We investigated the generating set and obtained the ranks of the two semi groups. These are some of the introductions. As we all know, in mathematics, whenever you have a set and you define a mapping from that set you solve, such kind of mappings are called transformations. If you attach composition of mappings as operation on that transformation, you end up having the semi-group called semi-group of transformations. Now let Xn be a finite chain, 1 to n. If we allow the domain and image of Xn to be just arbitrary subsets, not necessarily the whole Xn, such kind of mappings are called partial transformations. And their collections give us a semi-group called partial transformation semi-group, which we usually denote by Pn. If you restrict A to be, I mean, the domain of the mappings to be the whole Xn, then they give another semi-group called full transformation semi-groups, which we denote by Tn. Also restricting the domain of the mappings to be strictly subset of Xn, we have strict partial permutations. And if they are subset of Tn, they are called singular elements, which is it's one of the sub-semi groups that was presented by Sergio last week. A transformation is said to be order preserving, respectively order reversing, if for any 2 points you pick from the domain, if x is less than or equals to y, means image of x is less than or equals to image y. That means it's preserving the order. Then we call it order preserving. If it's reversing, the order is called order reversing. Of course, it makes sense to define order on the points since we are dealing with chain. And chain, we know there's special order on it always, and all elements are related to each other. So mapping is said to be contraction if it contracts the distance. That means for any 2 point in the image set, the distance between the 2 points is less than or equals to the distance between the three images. And we call it a distance preserving or an isometry if it preserves distance. some of these properties are most at times closed. So since it's closed, they also form subsemi groups of Pn. For example, a set of all order preserving elements form a subsemi group of partial transformations called semigroup of order preserving partial transformations. The same with order preserving or order reversing. Order reversing alone cannot form a semigroup because it's not closed. Whenever you multiply two order reversing, you always end up having order preserving elements. So, but if you take their union with the order preserving, you have a semigroup order preserving or order reversing. Same thing with contraction is always closed, is also closed. Therefore, their subsets form a subsemi group of Pn. As in all, in most of mathematical settings, whenever you have a structure, if you take intersection between two structures and they happen to be non-empty, such intersection gives you another structure. Same thing with semigroups. For example, if you intersect between partial transformations, other partial transform with partial contraction mappings, you end up having a semigroup called semigroup of order preserving partial contraction mappings. Also, the intersection between order preserving or order reversing with the contraction gives you order preserving order reversing partial contraction mappings. Same thing with OCTN, ORCTN, and even the isometrics. These are some of basic definitions we have. The first one is convexity. If A is a non-empty subset of Xn, then we said A is a convex subset. If you take any 2 points in A, all elements between those 2 points are also belongs to A. Another way of saying it, there is no missing point between any two intervals, 2 points. You have the whole interval in A. So such kind of if A satisfies this property, A is called convex. A generating set, when we have a semigroup and that there is a subset of semigroups that generate the whole set, meaning whenever you take an element from S, you can always write it as a finite product of elements of A, then you say A generate S. If A is the least number of elements that can generate S, then we say A is minimal generating set of S. Every semigroup has a generating set. The most obvious one is the semigroup itself, the set of the semigroup itself. But most of the times, you're not interested in the semigroup itself. You always want to have a smaller number of elements that can generate the whole structure. So whenever you're storing generating sets, we are trying to investigate to see if you can have smaller number of elements to generate the whole structure. As I think last seminar by Dr. Imam, we had that generating sets play a crucial role in studying semigroups because it gives you some advantage of studying a fewer number of elements than considering the larger set. Also, if you talk about ranks is nothing but the cardinality of the minimal generating set. So whoever studying rank is actually studying generating set of that semigroup because it entails about I think 99 point something percent of the work. Once you obtain the generating set, you are able to obtain the minimal generating set. Then all you need to do to find the rank is to count the number of elements. I think counting is not a big deal. For example, to see what we are talking about, let's take a set of all possible colors we have in the world. For example, uh, you can imagine how big that set is. To work with this larger number of elements, if you look at what generate this set, we can say just the primary colors, as we are always been taught. Primary colors generate the whole colors. Now there are only three. So and if you look at this set of colors, it's close actually because if you take any two color, you combine them, you end up having, the mixture, you end up having another color. And it doesn't matter the order of the mixture. If you have three colors, you want to mix them up, mixing the first two or the last two before the first one always gives you the same result. So you can see as the set of colors, it can be seen as a semi-group. but I don't know whether it's monoid or not because I doubt if there's any something like neutral color. White is not neutral anyway. But if there's neutral color, then S can be monoid also. Another example is the set of integers with respect to addition. The semi-group, of course, and is even infinite. You can see it's only generated with only two elements, one and minus one. That's with respect to addition. We have other the concept of rank uh, is can like be likened to many other concepts in other fields of mathematics. For example, in vector spaces, we can see generating set as spanning sets. You say a set span the whole space if every vector you pick, you can express it as linear combination of elements in the span set. Same thing here we have in generating set. While bases are also similar to what we call minimal generating set in algebra. Dimension is nothing but number of the bases, which is of course the rank in algebra. Group relations are very, very important in studying algebraic, whether it's algebraic, combinatorial, or rank properties of any semigroup. We had enough lectures last time with, I think, Dr. Imam Zubair about group relations. So I'll just go to the next slide and talk about the results of Zhao and Yang, which is basically characterizing group relations in the semigroup under investigation. The first result says let alpha and beta belongs to the semigroup of OCPN. If the height of alpha is 1, then alpha and beta are L related if and only if they have the same image. And if the height of alpha is greater than or equals to 2, then alpha and beta are L related if and only if they have the same image and alpha is kernel related to beta. The second result is about the R classes, R classification, I mean. It says if alpha and beta belongs to OSPN, then if height of alpha is just 1, then alpha and beta are R related, and only if the kernel of alpha equals to kernel of beta. And if the height of alpha is greater than or equals to 2, then alpha and beta are related if only if the kernel classes are same and alpha is image related to beta. Please, the term kernel related and image related, if one needs more clarification on that, can check the work of Zhao and Yang. The distance is here. Uh, Let me notification, sorry. Okay, thank you. So this is the reference. The last result is from the work of Ali et al., which gives us the semigroup ORCP. You remember we are dealing with two semigroups here, OCP and ORCP. It's also similar to what we have seen in the work of Zhao and Yang, because the work is the extension of the work of Zhao and Yang. These are some of the literatures. Over the years, many authors have worked a lot on the many sub-semigroups of RPN, ranging from the algebraic, combinatorial, and rank properties. This includes Hawe, Thomas and Hawe, Mazbuchuk, and Gayunching. Garba also studied many semigroups, ranks of many semigroups. We only quoted three here. While this study was going on regarding some sub-semigroups of PN, the contraction mappings, which is relatively new compared to other bigger subsemi groups of PN, receive less attention. Uh, Until recently, when Zhao and Yang study the algebraic property of OCPN, where he give regularity, characterized unit relations and regularity in the semigroup. Additional study combinatorial properties of some subsemi-group of OCTN, where they give the order of the semigroup OCTN and the order of idempotence there, as well as ORCTN. Garba in 2017, Garba et al. Study group relations on the semigroup CTN. Same year, Omar et al. Also investigated group relation in CTN, where they also give regularity and and they characterize anyway the green solutions and they study regularity elements there. The work was extended by Ali et al., where they consider the bigger semigroup CPN. They also, among of other things they study there is the green solutions and regularity elements. In 2011, Kahinde et al. Studied control properties of the semigroup of order decreasing partial asymmetries. El Corusi et al. In 2014 and 2016 respectively study algebraic and commensurate respectively of the semigroup of partial asymmetries as well as the subsemigroup or DPN. In 2018, Ali et al. Extended the later result of the El Corusi of 2016 by considering the ideals of the semigroup of ODPN. In the work, they were able to also study important elements on the semigroup of ODPN. Ike et al. Also study some ideals of the semigroup of ranks of some ideals of the semigroup of the partial isometries. Somani also in Semia study algebraic properties of the semigroup order preserving partial isometries, but on a restricted range. Ranks of contraction mappings, a lot of work has not been done in studying ranks of contraction mappings and the subsemigroups. Although 2020 Toka study rank of the semigroup of OCTN and ORCTN. The work was extended by Leila Bouguet to consider ideals of the two semigroups. Ali et al. In 2021 study nilpotence in the semigroup of OCPN and OCIN, where they also gave the rank of the two subsemigroups. Here is first part of our main results. To begin with, we define KP as to be a set consistent of all elements of IP, and OCPN subscript NP to be the two-sided ideal of OCPN consists of all elements less than or with height less than or equals to P. We have the first lemma saying KP is contained in the semi is generated by elements of K plus 1 for all ranks of P from 1 to n minus 2. Before I want us to understand that this lemma is very important. It was displayed last week. Similar lemma like this was given by Sagir during his presentation. Sometimes we are studying generating set. In most cases, you try to see if you can establish this result because it is very important. Same group of transformations are something like with layers, like we can call them layers. We have the height 1. If there is a empty map, it's going to be height 0. We have height 1 up to height n in some cases. And if you're dealing with singular elements, that are like sync n, similar to the kind of semi-groups presented last week, you have up to height n minus 1. But in most cases, semi-groups you can find from height 0 up to, if you are especially dealing with partial transformations, up to height n. So if you can if you can establish this result saying that for any height p, those elements can generate the lower elements p minus 1. P minus 1 can generate p minus 2. Once you can establish this result, all you need to do, you go to as high as possible, and most of the times at height n minus 1, since height n are the symmetric group, which cannot generate anything lower because the symmetric group is closed. So you go to up to height n minus 1. If you investigate generating set in that layer, then you are sure that they can generate all the remaining elements. So it simplifies the work actually. The proof is lengthy, is a kind of case-by-case analysis, since we have order preserving attached to it, we have contractions, so you have to be careful with the cases. So it's lengthy anyway. When we after the presentation, we can have the right of go through the proof if you want. The next is corollary following from lemma 4, saying that the elements at height n minus 1 generate the two-sided ideal OCPn n minus 1 for all n greater than equals to 3. The proof is as follows. We can see from definition we have by lemma 4, they're saying Kp is generated by kn minus 1 for all p from 1 up to n minus 1. And this means if you take the union also stays inside the generating semi-group generated by kn minus 1. And the union is nothing but the two-sided ideal, because we are saying here is less than or equals to, and so taking the p's from 1 up to n is what this is referring to. So we are saying the whole this is contains here. We also notice that from definition of our KP with this kn minus 1 stays inside this, and since OCP and n minus 1 is a semi-group on its own right because it's two-sided ideal, therefore it's a semi-group. So it contains kn minus 1, it must contain semi-group generated by kn minus 1. So we have this inclusion and this one, therefore equality is established. These are some notations we use to describe elements of kn minus 1. Uh, we should observe that in kn minus 1, we have two types of elements. We have mappings that are full and with defect 1, and mappings that are one-to-one, where one element is missing in the image set, and another also one element is missing in the domain set. So we denote by this pi I plus 1 to mean those are full maps that have, of course, we've seen last week in Sangeet's presentation that at kn minus 1, those full maps will have singleton kernel classes with the exception of one that will have two. So those elements that have two, those are the elements because our own is partial. So it's going to be these are the kernel classes with two elements. The other ones are the singleton. So what we are saying actually is if you see pi 2 3, it means this element is having 2 and 3 as having same kernel class. This one meaning one is missing in the image set. And here, if you see n here, these are the alphas are the one-to-one elements. So alpha n means n is missing in the domain set. The one is one missing in the image set. So this is how we use to describe the elements so that we have, whenever we write n, we know what we mean by writing the elements. And this helps us to construct this table. This is a table of all elements of kn minus 1. They are written in such a way that the row classes represent the R classes, while the columns represent the L classes. If you can count the index running from 1 to n minus 1 for this one and that of j, you can see that we have about 3 into n minus 1 number of R classes for of kn minus 1. And since when you are talking about generating set, it must cover all the R classes. Therefore, this lemma is saying the rank of kn minus 1 must be greater than or equals to 3 into n minus 1, because that's the number of R classes we have. So any rank you are going to talk about in any generating set must be, of course, bounded below by the number of the R classes, which is 3 into n minus 1. Proposition 7 is saying let G be a set comprising all these elements, then G is a minimal generating set of kn minus 1. Usually, issue of the proof minimal generating set have different ways. One of them is once we bound rank below, whenever we can have a generating set that has same element as the lower bound, then we prove it. Or another way, we prove what we call the necessity and the sufficiency. So it's necessary, it has to generate it, and sufficiently there is okay, only these are the G is okay. Any missing elements from the G cannot generate it. In this case, since we bound our rank below by 3 into n minus 1, once we can prove G has this number of elements, then it's a minimal generating set. So the first part of the proof, if you look at the table, this table, sorry, look at this table, the elements we have there, some of them are missing in G. So once they can be generated by elements we have in G, then we can say G generates kn minus 1. And this is what we have here using usual normal multiplication of elements. So therefore, G generates kn minus 1. The minimality follows from the fact that if you count number of elements in G, you have 3 into n minus 1. So we can say G is the minimum generating set of kn minus 1. Theorem 8 is saying the rank of all CPN n minus 1, that two-sided ideal is nothing but C into n minus 1. The proof is as follows. From lemma 7, we establish the rank of k into n minus 1 is 3 n minus 1. Now, by corollary 5, you remember we said OCPN n minus 1 is nothing but it's generated by elements of k n minus 1. Therefore, rank of this automatically is going to be rank of the OCPN n minus 1, which is 3 into n minus 1. We have corollary 9, which says the rank of OCPN itself is 3n minus 2. Uh, of course, we can see that if you remove elements of height n minus 1 from OCPN, what you are left with elements 5n. And because of the order we have on the semi-group, what is left there is only order preserving is only the identity element, this symbol 1n, which is our identity element. So therefore, the rank of OCPN is going to be rank of the two-sided identity OCPN minus 1 and the rank of the identity, which is the identity itself. So it's going to be 3 into n minus 1 plus 1. If you simplify, you end up having 3n minus 2. So we finish with the first part of the work, which is investigating rank of OCPN. We are going next to elements of ORCPN. We recall that we mentioned order reversing element, order preserving contraction mappings stays properly inside order preserving or order reversing because it is union of two type of elements, the order reversing elements and the order preserving elements. And as we mentioned earlier, that order reversing element is not closed under the operation, so it cannot be a semigroup on its own. But if you take the union between order reversing and order preserving, you again have a semigroup which is larger than OCPN. It's called order preserving or order reversing partial mappings. So this notation, we use it to denote the order reversing elements in the semigroup. In particular, we mean write this. We've seen earlier that without the asterisk, 1n is the identity. So with the asterisk, 1n mean the reflection of the identity. That's our order reversing. Observe that if you multiply this by itself, you get the identity element. 1 to n, n goes to 1, so 1 to 1, 2 to n minus 1 like this, we will have the identity. Now, let alpha star be order reversing element in ORCPN. We notice that if you multiply alpha star with this reflection of identity, you get some order preserving elements in the semigroup. Now, again, putting this reflection of identity in both sides, you also this becomes identity now. So you have only alpha star, and here you have some elements in OCPN multiplying this. So what this is saying is, if you take OCPN, any order reversing element you pick is a product of some order preserving with the reflection of identity. So we can rightly say now OCPN union, this element generate ORCPN. The next is proposition 10, which is saying if we define G as in proposition 7, then G union this element generate ORCPN. The proof is as follows. Number proposition 7 and corollary 5, we've seen that this G generates, because it generates Kn minus 1 and Kn minus 1 generate OCPN n minus 1, therefore G generate OCPN n minus 1. Therefore, and since we mentioned earlier that in OCPN, this set, if you remove this set, what you have left is only the identity. So therefore, G union the identity generate OCPN. Moreover, by the previous equation we've seen above, this one, equation 3, we are saying OCPN union this element generate OCPN. Therefore, since G generate OCPN, G union this element generate ORCPN. Theorem 11 is saying the rank of RCPN is 2, 3, n minus 2. Now, we remember the number of elements in G is 3 into n minus 1. So therefore, uh, and this element is only one. So 1 plus 3 into n minus 1, you get 3 n minus 2. We should observe that ORCPN, although it's bigger than OCPN, it's a larger set, they have the same rank. In the last part of the work, we've seen the rank of OCPN is 3 n minus 2, and here we're also saying the rank of ORCPN is 3 n minus 2. These are some selected references. These are some possible, I think, open problems. Uh, we mentioned earlier that the semi-group of partial construction mappings have a lot of open problems are yet to be solved. For example, although many studies took place regarding the ranks, those kind of semi-groups that have order, when these are those that without order are still open, like the CPN itself, the CTN, CIN, and the semi-group of order decreasing partial contractions. So also, there's need to study idempotent and quasi-idempotent of these semi-groups. Although we've seen we have a lot of algebraic studies were done for CPN as well as CTN. Some of the authors are here. The secretary himself with his co-authors, also Dr. Ayman Zubair and my supervisor himself. But the idempotent, we don't know whether we can ask this question: can CPN be generated by idempotent elements or quasi-idempotents? If not CPN, can CPN intersection the singular elements, that's n intersection CPN, just from n minus 1 downward? Same thing with the CTN. Although we know idempotence generates TN itself, though, but can it generate CTN? And we've seen from the work of Sagir last week, he did mention that in Garba et al., they were able to establish whether idempotents generate IN. Can they generate CIN is another question. We also have in the case of discipline. So these are some possible questions one can consider if you want to be part of those that are studying the semi-group contraction mappings. For the nilpotents, a lot have not been done there, although we did study nilpotents in other preserving partial asymmetries, which is also a subsemi-group of contraction mappings. And we also studied nilpotents is OCPN and OCIN. But there's no study that I know of based on what I've seen through the literature, the base of my knowledge of CPN or CIN or DCPN. Also, the combinatorial properties, although we know the chairman here, Adishola and Omar, I think, they study some combinatorial properties of OCTN. But also recently, I've seen the work of Omar and the Skellen, where they study the combinatorial properties of OCIN, ODCIN. But the CPN, CTN, and all these subsemi groups without order on them were not, I think, well investigated regarding combinatorial properties. So all these are open areas that need our researchers to come in. Thank you for listening. Thank you very much.
Thank you, Mr. MAJada, for the beautiful presentation. We are
Thank you, sir.
sincerely grateful for this compilation. It's not easy. It's not easy at all. The most exciting things about what you have done to me is the open problem, because the open problem tells you where the green areas are. It
Yes.
tells you, it tells our, even it tells, it teaches most of the teachers here the area where their students can work on. At
Yes.
times, it's very difficult to know where open problems are. But I could remember Professor Abdullah Huma around 2007. He did one research later published maybe 2000 and maybe 2020. I think about 15 years ago, he published an article that he called, I think, where he highlighted many areas of combinatorial problems. I
Mm.
think on OCTN, on the, okay, there was, at times at that time, we have not started contraction. He highlighted many areas in the other preserving, other decreasing, other preserving, other reversing, and some others. He called it something like layout something, layout
Some
article.
combinatorial,
Oh, some combinatorials. Okay.
mm,
Yes.
say some
I,
combinatorial problems in the study of symmetry inverse and some combinatorial
okay.
problems in the study of, I think, partial order preserving, something like that.
I think this is exactly what Dr. T. Imam did, I think, in his last presentation, where he highlighted about almost 50 areas of research.
Yes.
And this, it is not easy to identify where, if you are not familiar to that terrain, you can't know where people have worked, where they have not worked. On this, for someone to identify where problems are, is a research. And that was what Umar did in that article. It
Yes.
just affected some areas where on this OCT, and these are the results they've gotten. This, I think Dr. Timam did similar thing to what Umar did in his last presentation. And you equally did something similar because you have shown us where we can work on this thing. Thank you for this present. I wish you a very quick, successful completion of your program, so that by very soon you'll be addressed as a doctor of philosophy in mathematics. Thank you.
Thank you very
My members of